Welcome everyone. Today we're going to be looking at implicit differentiation. So we're going to start this kind of new differentiation technique, and it's for a very specific type of function. And then next time we're going to get to the related rates part of this. So let's start by just considering the type of function that we're going to be investigating here. And it's something we really haven't seen too much of. All right, so to kind of get going here, let's start with probably what we're used to. This is the thing that we see kind of the most. Let's start with our explicitly defined functions. So when we have an explicitly defined function, what does that mean? Well, we literally have y. We have our variable y, and it's explicitly written as a function of x. So this is probably the first thing you think of when we're talking about y being a function of x. This is what we see the most. So an example of what, something like this might look like is y equal to x squared minus 1. We have y, and we have this formula involving x, and it says y is equal to this formula of x. So there's this explicit formula right here staring at us. And so we know we're dealing with an explicit function of x if we have something where we see the y equals. So that y equals is stated. It's literally telling us what y is equal to. And so a graph, of this example is a parabola in this case. Okay, so that's what we're used to. That's what a lot of times when we think of functions and now differentiating functions, we think of working with things like this, where y is equal to something involving x. Well, this is an equation involving two variables. There's the y over here, and then there's the x terms all over on the other side. So there's two variables going on here, x and y. So we have two variables. Now what happens with the other type of function we're going to be looking at, and this is kind of the main focus of this lesson, is what we're going to call implicitly defined functions. And so let's start with kind of what an example for something like this might look like. And it's going to involve an equation involving both x and y. But now the key difference here is kind of a little example based on this graph below, x squared plus y squared equal to 4. The key difference is we're going to view y as a function of x, but now this is not in the form y equals. But we're still going to treat y as a function of x. Even though we don't have an explicit formula literally telling us, like over here, what y is equal to. Maybe we could solve that equation for y. Maybe we could. Sometimes we can't, though. But we're still going to be able to treat y as a function of x, even though we don't have an explicit formula. So this word implicitly, you can kind of think of this as like implied. It's not specifically stated, but it's implied. So we're going to assume y is a function of x, even though we don't have it in that correct format. So when we look at these two types of functions, it's still going to make sense in both cases to talk about the derivative. So we're still going to be able to talk about the derivative dy dx. And in both cases, what the derivative does is it gives us the slope of the tangent line to the curve. So what we've done in the past so far is we've had things like this, like a parabola, and we've looked at points on the curve and we've figured out the slope of the tangent line at those points. Well, we're going to be able to, and we're going to see, how do we calculate the derivative dy dx for equations like this, where we don't actually have y equal to. And the result is still going to get us the slope of that tangent line. Now you may be wondering, as you look at this, maybe you've heard of the vertical line test. So this is a way to quickly check if an equation is a function or not. And so for this parabola, the way the vertical line test works is if you draw any vertical line, it only crosses the graph once. And so you can see that you can kind of repeat this over and over, and we're only intersecting, each vertical line only intersects the parabola once. So this just outright passes the vertical line test. Now it doesn't work so well over here with this equation x squared plus y squared equal to 4. The graph is a circle, and if we were to draw a vertical line, well, a lot of these vertical lines are going to actually intersect that curve more than once, twice. And so the way we treat these implicitly defined functions is we only look at a section of the curve. So that's kind of we're not going to worry too much about that, but just something to keep in mind. So for instance, we might only look at like a little section of the curve here. Or maybe we could do a little bit better and look at maybe like the top half of the circle here. And that is a function. That does pass the vertical line test. So this equation, these equations that we're going to be working with, if we kind of restrict to sections of the curve, then we can view y as an implicitly defined function. All right, so this is the idea here. We're going to see how to calculate the derivative for these types of equations where we don't actually have y equal to. We don't have the solution there for what y is equal to. We only have these equations where the x's and y's are kind of all mixed together. And so the way we're going to do this is, the way this technique of implicit differentiation works is we're going to look at the equation and we're going to kind of think of each variable slightly different. So for an equation involving two variables, if x and y are the two variables, we're going to start by treating x just as it is. We're going to treat x just as a variable. Now, y is going to be slightly different because we're treating y as a function. So y is going to be a function. But we're also going to think of it as a variable as well. So when I say this word function, think of it as there's going to be some kind of x terms hidden inside of it. All right, so let's see how this, and as we come back up here, we're gonna add to this page, but let's start with an example. Let's start with example 1 to see how we can calculate the derivative dy dx given this equation x squared plus y squared equal to 4. And the technique that we're going to use is called implicit differentiation. So let's start by just kind of looking at the first step here for implicit differentiation. What we're going to do is we're going to apply the derivative of each term. We're going to apply the derivative to each term. All right, so let's do that. So let's start by writing our equation. X squared plus y squared is equal to 4. And we're going to apply the derivative to the first term, derivative to the second term, and then basically everything. So we'll also apply it to that 4 on the right. All right. So a lot of the work here is a lot of the calculus work is going to come in step 1. And then the rest of this is going to kind of involve solving for the derivative. All right, so let's see how we're going to calculate each of these. And for this first one, this first term only involves x. So we're treating x just like a regular variable. So the derivative here is just going to be like what we normally expect. 2x in this case. And then we're going to have plus. And then we're going to look at this y squared term, the derivative of this y squared term. And this is where it's going to get a little different. So we're going to hold off on that for just a second. Let's leave a little bit of a space. And then over on the right side, we're differentiating a constant. And this is also just like normal. Derivative of constant is 0. All right, so when we're differentiating just an x term, because we're trying to calculate the derivative with respect to x, we're treating x just like a regular variable. And so that means we're just going to differentiate it just like we normally would. So let's go back up here. Since we're treating x just like a regular variable, if we have a term in our equation that only involves x, we're just going to differentiate it like usual. All right. Now, what about that y term? What about a term involving only y? Well, there's going to be 2 things that we do. The first thing we do is we're going to differentiate like usual. Okay. And that really comes from the kind of the variable side of y here. So y, it is a variable, so we're just going to differentiate it like usual. But we're also treating y like a function of x. So we're going to do something else. We're going to multiply the result by y prime. All right, so let's see how this is going to look for that y squared term. And let's try it out. We're going to differentiate y squared. And as kind of like a motivating example, let's look at this function f of x. So let's forget about implicit differentiation for a second. And let's look at this function x to the 4th plus 3 squared. How would we differentiate this? Well, we would calculate f prime. And we would use our general power rule, which is the chain rule, as we've seen. So what would we do? We'd bring down the 2. We'd keep x to the 4th exactly the same. We'd subtract 1 in the exponent, so we'd get 1 there. We won't write the 1. And then we take the term that's inside the power function, and we're going to multiply by y prime, or the derivative of that. So we take this inner term and we multiply by its derivative. And this is chain rule. And then we would go from there. Well, when we differentiate y prime or y squared, so this was some function being squared, x to the 4th plus 3 squared. Well, now let's calculate the derivative of y squared. What are we going to do? So let's calculate the derivative. Well, we'll kind of differentiate this with power rule just like we did up here. So we're going to bring down the 2. We'll keep y exactly the same, just like we did up here. And then also, just like before, we're going to subtract 1 in the exponent. So we'll have that hidden exponent of 1. And then, just like before, we're going to multiply by the derivative of those inner terms. So this is chain rule, and this was chain rule down here. So we've kind of just shortened this up, and we're viewing y as a function of x. It's very similar to this x to the fourth plus 3. We're viewing that x to the fourth plus 3. Well, that definitely is a function of x, but we're also viewing y as a function of x. So the chain rule tells us that we're going to differentiate the y squared term just like we normally would to get 2y, as if it were just a power function, but then we're going to multiply the result by y prime. And that's what we're doing. All right. So let's go back down and use that. We're going to differentiate this y squared term and differentiate it like usual by the regular power rule. So 2y, and then we multiply that result by y prime. All right, so that's all the derivatives that we need to do. Now the rest of our steps here for calculating or using this technique of implicit differentiation are going to be solving for this y prime, getting all the terms on the other side. We want y prime all by itself. And so let's read through the steps here of how to do this. Step 2, we're going to move all the terms with y prime to the left-hand side, and then we're going to move all the terms without y prime to the right-hand side. All right, so let's look. What term has y prime in it? Well, this whole thing right here, there's a y prime. And then what doesn't have y prime? Well, that 2x. So anything with y prime, we're going to keep it on the left. So this is going to stay over here on the left. And then anything without y prime, we're going to move that over to the other side. So the way to do that is I'm going to subtract 2x from both sides of this equation. So I have 2y times y prime, and then that'll be is equal to negative 2x. And where does that put me? Well, that puts me at step 4. I'm ready to factor out y prime on the left. Now, sometimes there's a little bit more going on, but this is already nice and factored for us. So we have 3 different factors here. We have the 2, we have the y, and then we have y prime. So basically, I'm going to take everything that isn't y prime, in this case the 2y, and I'm going to move that to the other side. I want to get y prime by itself. And so when we have multiplication, the way we can move things to the other side of our equation is by division. So I'm going to divide both sides by 2y. And so when we do that, we get y prime is equal to negative 2x over 2y. And if we clean this up just a little bit, we have y prime is equal to negative x over y. And that's our derivative. And that's precisely what we finished up with. We factored out the y prime on the left. So there it was, all nice and factored out. And then we divided both sides by the other factor, which in this case was that 2y. And that's really the process for implicit differentiation. And so what we're going to see is we're going to just use this technique for equations with more going on. And what can happen where more is going on essentially is, this equation wasn't too bad because we had really 3 distinct terms here. We had the x squared, only had x's. We had the y squared, only has y's. And then we had this constant here, that was no big deal. So we saw how to differentiate terms involving only x or terms involving only y. And what we're going to see in later examples is what do we do if we have terms that have both an x and a y in them. And the good news is we've already have the rules to help us out. So if we have a product, so if we have x times y, well, we're going to use product rule. So an example of something where a term that you would have to use product rule on would be something like x squared times y. if we have a fraction, well, then maybe we have to use quotient rule. So maybe that would be like an example of x cubed over y squared. So it's a term involving both x's and y's, and they're being divided. There's a quotient, there's a fraction. So we'd have to use quotient rule. Or maybe we have a composition. So maybe we have to use chain rule. So an example like this might be x plus y squared all cubed. So this term, this is one big term, and there's both x's and y's in here, but there's this inner function part and then there's this outer function part. And so we'd have to use chain rule. So that's what we're going to be looking at. We're going to kind of spice up our equations here with these more complicated type terms. And we're going to see an example of that in class next. All right, but let's just finish this one up. So the first part was just getting the derivative. And then once we have this formula for the derivative, we can do all of the usual things, you know, finding the slope of a tangent line, finding the equation of a tangent line. Now, what's slightly different here is the derivative. This formula for the derivative involves both x's and y's. And that's perfectly okay, because our original equation involved both x's and y's. So let's just see how we can use that derivative to find, say, the slope of the tangent line. So for part 2, let's find the slope of the graph, really the slope of the tangent line, at this point and then at this point. So let's start with the point 1 comma square root 3. So when we look at this, the x-coordinate is 1. So just keep that in mind. X-coordinate is equal to 1 for this point. And our y-coordinate is equal to the square root of 3. And so we can find the slope by just taking our derivative, that nice formula we just figured out, and we're going to evaluate it when x is equal to 1 and when y is equal to square root 3. And so this big vertical line here just means evaluate. All right, so what was our formula for that derivative? It was negative x over y. And we're just going to plug in x equals 1 and y equals square root 3. So in this formula, wherever I see an x, I'm just going to change it to 1. And wherever I see a y, whoops, forgot the 3. Wherever I see a y, I'm going to plug in square root 3. So when I do this, I end up with negative 1. So I place the 1 in for x over square root 3. And if I wanted to, say, rationalize this fraction here, not really necessary here, but, you know, sometimes helpful, I could multiply both the top and the bottom of this fraction by square root 3. Just to get the square root out of the denominator. But again, perfectly fine if you want to leave it like this. So I end up with negative square root 3 over 3. And this is the slope of the tangent line, the slope of the curve. All right, what about the other point? Well, the other point is 1 comma negative square root 3. And here the x-coordinate is 1, but the y-coordinate is, well, negative square root 3. So the way we're going to figure out the slope in this case is we're still going to evaluate that same derivative formula, but now we're going to be plugging in x equals 1 and y equal to negative square root 3. And so when we do this, I'm going to plug 1 in for x, so I'm still going to get the negative 1 up there on top, and then negative square root 3 on the bottom. and the negatives are going to cancel, so it's a double negative, so this just ends up being positive. And then if I wanted to rationalize the same way, we could simplify this to just square root 3 over 3. So this has a positive slope, essentially. And you can kind of see, why are we looking at the slope at 2 points? Let's go back up to our graph here. So at the point 1, at this point 1 comma square root 3, we found that our slope was negative, so we figured out the slope of the tangent line. Well, for our circle, there's another point, and we just figured out the slope of the tangent line down there, and we saw that it was positive. So we were able to investigate the slope of our tangent line at each of those points. One was negative, one was positive. All right, so that's the idea with implicit differentiation. So in class, we're going to be just kind of doing more practice, and we're really going to spice things up in example 2 here by looking at an equation. So it's going to involve both x's and y's, but now we have a product. So we're going to see how to do that in class. So we'll see you then. Bye-bye.